I think now my main screen should be shared.
Yeah, it looks good.
Okay.
Yeah, we can get started. Thanks everybody for joining, and thanks Soroush for giving us this talk. We are about to start. I just want to emphasize that the attendees that please feel free to ask questions during the presentation. You can either unmute yourself, or you can also, if you type your question in the chat, I will make sure to address them with Soroush. With that, Soroush, floor is yours. Please feel free to start when you're ready.
All right, thanks. Before I dive into the details, I think that maybe it's better to have a TLDR version of the work. So basically, what is conformal prediction? Conformal prediction is a method that wraps around any model with a black box access, and it returns a distribution-free prediction set. So it doesn't look at the distribution of the data, distribution of the labels, or the model mechanics. It wraps around any model, and it returns a prediction set at the end that is guaranteed to include the true label with any adjustable 1 minus alpha probability. So let's say, for example, now 1 minus alpha is 90%. So you define this on a model, you get prediction sets, a set of labels that it's guaranteed that in 90% of the time, the true label is inside the set. But this guarantee at the end is for the clean data. So it's for in distribution points and the points that are not perturbed in any case. So an adversary or nature noise can cause this guarantee to be invalid. So as an adversary, I can perturb the input in such way that the guarantee of 90% in practice works like 30% or any other based on the magnitude of the noise. So as a defense, we can use robust CP, which maintains the same guarantee, and now even for the worst case perturbed input. And our result, which I will also discuss it at the end of the discussion, is that we create smaller prediction sets. So basically have less labels in the set, which makes it more useful. And at the same time, in a very faster way in terms of computational time, and with the same guarantee for the worst case input. Also, in addition to that, we address the label poisoning and feature poisoning, which in this talk, I will talk just about the feature poisoning. So first of all, before...
Sorry, can I ask you about the previous slide?
Yeah, sure. Yeah, sure.
Previous slide. So, so you mentioned that the guarantee will break if one adds noise. Will that happen? Will the guarantee break even when the noise is IID?
So that's the point. As long as the output, as long as the test input and the calibration data, which we define the conformal prediction based on, are exchangeable, the guarantee is maintained. Also, you can define some variants like probabilistically robust conformal prediction that accounts for IID noise as well. But now, in this case, we are talking about the worst case noise, which could be, I don't know, not IID noises or adversarial noises, which are perfectly crafted based on the architecture of the model and the parameters, and basically are defined in such way that they want to break the guarantee or break the prediction result. Did I address that question?
So, did I get this right, that the guarantee will not break if the noise is IID? It will only break if the noise is designed in a special way to break.
No, it could also break if the noise is IID.
Okay,
it's the point. Yes, but there are easier methods, like there are methods based on quantile of quantile that also try to address the random noise as well. But then the probability is also a probability on the noise. So now the probability that we have, this is a technical thing, but maybe I can tell it in a clear way, that the probability is now on the calibration data and the test data. But then the probability in those methods would be on the calibration data, test data, and the noise.
Okay. All right.
Okay. But
Yeah.
now this method basically doesn't care about the noise. It works for any bounded worst case noise.
Right. Okay.
All right.
Thank you.
So anytime. So now before diving into the robustness, let's first start with a motivation and conformal prediction. So assume that you have a model. It could be any model, any complexity. It doesn't matter. And it's a classification model for the moment. And this model at the end gives you some score. It gives you some, I don't know, logits or softmaxes. Now assume that it's softmaxes. And now how do you use this model? One case is that you can say, I just take the top class, I take it as a prediction, and I use it. But the point is that this top class prediction is not a trustworthy source always, because the accuracy of the model is not known prior to the labels. All right, and basically this softmax or other scores that you define here could be also miscalibrated. So it could be a false prediction with a really high confidence. But as an alternative, you can define conformal prediction. So you can define prediction sets instead of one prediction, but you can guarantee to include the true label in 90% of the times or 95% of the time. So this 1 minus alpha is adjustable, and you can just adjust it to some degree. And interesting work that I see also in this ICML conference was that there was this study that they used a human decision. They tried to capture the human decision when given the top class label, when given the top K class labels, or conformal sets. An interesting result of their work was that when people have the conformal prediction sets, and then they are asked that what is the true label, decide what is the true label, their response was quicker and at the same time more accurate, which is really an interesting result, because for me also it was like, how can it be used in deployment? How does it behave in deployment? But it's also a really nice experiment that I see in another paper that I cited here. So now how to define these conformal sets. It's a really simple algorithm. So you have a calibration data, a set of data points that their labels are not seen by the model during the training. So the model is not biased on those inputs. And in a simple step, you have the score function, which is basically the output of your model, or even if you have any complex score function defined based on that, whatever score works. So you have the score function, you evaluate the score function on each of these calibration points on the true label, and then you take the alpha quantile of these scores as your acceptance threshold. Now, during the test time, you again evaluate this score function on all labels for the test point and take those that are above this acceptance threshold. So basically, it's really simple to apply. And this prediction set that I defined here has the 1 minus alpha guarantee. But now, another interesting thing is that the predictions can break easily. So assume that you have a predictor, a model, and you can see that now I have an image of a panda, and I gave this image to the model, and I received the label panda with 57% confidence. And now I can add a really small noise, which if you see here, it's not a random noise, it's clearly crafted, but I can add a really small magnitude of this and get a totally different classification. So basically the model is not robust to a noise even with this really small magnitude of 0.007. And you can see that the model with this noise basically misclassifies with a really high confidence. So just to give a gist of how to design such noises, because these are adversarial noises, these are not random, imagine how you train the model. So you have a loss function, you have a model, you run a forward pass, you pass the data to the model, you get some output, you compute some loss, and the whole process is differentiable. and you get the derivatives with respect to the model parameter, and you then ask that in which direction should I go to have a smaller loss. So the same approach, you can design an adversarial noise. You can say that I keep my model weights fixed, and now I try to find the derivatives of the loss with respect to the data instead. And then you can say that in which direction should I move my data point, which is also a multidimensional vector, in which direction should I move it such that I increase my loss. So again, the same approach, you use the gradients and you can define this noise that basically breaks the model. And now let's have the same example in the realm of conformal prediction. So this is my prediction set for the image of these dogs. So the label is dog. I have a prediction set, which basically is cat, wolf, and dog, because those prediction results passed this acceptance threshold, which was basically the alpha quantile of my calibration points. And now an adversary can add a noise to it. And in the adversarial setup, they can move this score function, they can move this score for the true label below this acceptance threshold on the left side. So then if I can break each entity of each data point, then I can break the guarantee also the same way. Another scenario that an adversary or noise can break the system is that as an adversary, I don't want to change the test points. I don't want to change each test point, but I want to change the calibration points. So I can add the same noise to the calibration set and basically make the conformal prediction miscover many points. So before we dive into how to make this conformal prediction robust, we should go with a bounded perturbation assumption. So basically what we say is that we assume that the perturbation is in such magnitude that the perturbed point and the clean point are close to each other. So for example, I can say that for images, the norm of this difference is within some radius in the L2 norm distance. Or even for graphs, we can assume that the perturbation is sparse. So assume that I'm adding noise to the edge index, so I can at most add RA edges or remove RD edges. So these are the bounded perturbation scenarios that we mentioned. Now, how we can make the conformal prediction robust. So let's again recall the conformal prediction setup. So in this setup, I have a quantile, which is basically the alpha quantile of all these points. And my test point for the true label is on the right side of this quantile with 1 minus alpha probability. But now, as an adversary, I can change this input so that the score goes below this quantile in the rejection region. Okay? I will tell you how, but now assume that there is a way to upper bound this score within this bounded perturbation. So I move back to the slides. I call this B of R. I call this all possible perturbations around this point. And now assume that I can bound the score for any point inside this region. So assume that I'm working in an L2 perturbation. There is this point and there is this ball around it, and I can find the lowest and highest score, or an upper bound or lower bound for that, so that I know that within this region, the score will remain the same. Now, if instead of taking the score itself, if I use the upper bound around that, I can again maintain the guarantee. How? Okay, so I receive the perturbed input, I look at its L2 ball, and I find an upper bound. But since the test point is also within the same ball, so the test point is inside the bounded perturbation region of the perturbed point, then the upper bound for this region is also an upper bound to the test score. So if I use the upper bound, if the test score was covered, this upper bound would be also covered. So with that, I can again maintain the guarantee because I know that for all those points, that I was covering the result, I also now cover the result with this upper bound.
Sorry, if I may ask a question
Yes,
here. So in
yes,
setup, are you assuming that the calibration instances are
are
noise-free?
clean. Yes, exactly. So I assume that the calibration instances are clean. But later, so if I assume that those are perturbed as well, this is a poisoning scenario, and I will also address how to solve
Okay,
that
so
problem.
assume calibration sets is clean. You are given a test point.
Yes,
You assume that it may have noise. Okay.
yes. Or it may be perturbed in an adversarial way, yes.
It may be perturbed in an adversarial way, but you
Mhm.
don't have the label for the test point,
No,
right?
we don't have the label, yes. So we run this upper bound computation on each label. That's the point.
Okay. Yeah, maybe I will catch up later. Please, yeah, feel free to continue. Maybe I will catch up later.
Okay. So I just as a follow-up discussion, so I have a point that is perturbed, and now I find the upper bound on the score for each of these labels. So for Y1, I find an upper bound. I test whether it's above the quantile or not. I find the Y2, Y3, Y4 to the end. And for each of these labels, I use the upper bound. But I know that for the correct label, if it was on the acceptance side, also the upper bound on that label is also above the acceptance because it's more than even the test points score for that label. So with that, I can guarantee that still this upper bound results in a higher than 1 minus alpha coverage.
What is that upper bound?
So this upper bound is an upper bound on any score within this perturbed points possible perturbations. So in normal certificates, in normal setup, we assume that the test point is clean, but now I know that it's potentially perturbed. So instead of looking at, for example, assume that I have an R radius around the perturbed point, I know that since the test point is also within the distance of at most R, so if I find an upper bound on any score within this region, the upper bound also is higher than the test point.
This is an upper bound on exactly what? Maybe I should have asked that question. This is
yes.
on.
So this is an upper bound on, so assume that we are now just looking at label Y2, for example.
Okay.
And now I have this perturbed point. It on its own has some score. But if you look at any point in R radius around it, there are different score values, and I want an upper bound on all of those.
Oh, I see. No, okay, I see.
All right. So
it's an upper bound on scores that the point can achieve as long as it's within that circle.
yes, exactly. So if you look at any score within this circle around the point, then if you find an upper bound on that, then this upper bound is also higher than the score for the test point. And then we can just use that as...
Each plausible label, Y1, Y2, has its own upper bound.
Exactly, yes.
Okay. All right, thank you.
Anytime. So the point is that the certificate is on the confidence score of each label. Okay, so the upper bound, sorry, I said certificate. Later I will go with the certificate, but now it's on the upper bound of each score. Now we can assume that there is a black box or oracle or something that gives us these upper bounds and lower bounds, but later I will say that how we can compute those things. Okay. All right, so this was an approach that gives us a robust CP, but it works in the calibration. It works in the test time. So we should run this procedure on each test input and on each label of test input. So intuitively, now we can get that this process could be a bit also time consuming because so for For some data set like ImageNet that it has 1,000 classes, I need to compute 1,000 upper bounds for each test point that I receive, and it's a bit time consuming. So another approach to do so is to run the evasion robustness in the calibration time. So I have n calibration points, and I want to compute this acceptance threshold. Instead of computing this alpha quantile on the scores, I take the alpha quantile on the lower bound scores for each of these inputs in the calibration points and for the true label. So again, I rephrase in the previous setup, I assume that I have computed the quantile on every score, and every calibration point is clean. I compute the scores in a trivial way that I was computing it before. And for the test input, for the test point, I compute the upper bounds. But now, instead of doing that, I say that in the calibration time, which I have n different samples and n different true labels, just for the true label, I compute a lower bound score, and I compute the conformal quantile, or that acceptance threshold that I mentioned, on the lower bounds on each of these calibration points. And now, again, when I received a test input, which could be perturbed in some cases, I don't need to compute any upper bound. The perturbed point its own is covered. Why? So if you look at the diagram, you can see that for each calibration point, I'm looking at the lower bound. And the whole conformal prediction guarantee is based on the fact that calibration points and the prediction point and the test point are exchangeable. So their scores are exchangeable. And now this operation that I have done makes the whole system exchangeable with the lower bound score on the test point. So again, to rephrase it in a clear way, I have the lower bound on each calibration score, and these lower bounds are also exchangeable with the lower bound on the test score. But I know that for the clean test, my lower bound also is a lower bound for the perturbed input, because the perturbed input is within this bounded perturbation region around it. So I know that with 1 minus alpha probability, the lower bound score around the test point is covered, so I only need to compute it for the perturbed input. I only need to compute the normal score for the perturbed input, and this score is higher than the lower bound, which was exchangeable with these n calibration points, so again has the same guarantee. Is there any question on this part? Or I heard something, but I cannot read it. Can you read it?
Christian, please go ahead.
Yeah, sorry. I think there is a point that I missed. Sorry. I just want to understand clearly. I think for the second step, the second part that you are trying to adopt regarding the calibration set, you see that you are trying to now consider the lower bound, but I'm not sure to understand that point, because at that level, are you considering that the point part of the calibration set are also, I mean, there is also noise there in order to be able to...
That's a really good question. So again, I'm assuming that all the calibration points are clean, but now if I look at the lower bound of each calibration point, okay, so assume that I define a new score, that this score is basically the lower bound around each point. Okay, so the lower bound around all perturbations around each point. So the clean calibration points and the clean test point are exchangeable.
Yes.
Right? And the score, the lower bound score of clean calibration points and the lower bound score of the clean test point are also exchangeable. Yes?
Yes.
Sorry, if I may ask a question here. Will that be...
Yes?
No, you know what? Go ahead. Sorry. Go ahead. I will keep my question.
Okay, so the lower bound score on the clean calibration points and the lower bound score on the clean test point are also exchangeable. So it means that the lower bound on the clean test point is after the acceptance threshold with 1 minus alpha probability. Is it right?
Yeah.
So now I know that for this test point, assume that the lower bound is after the acceptance. So the lower bound is inside this acceptance area. So I know that this lower bound is lower than any score for any perturbation around this clean point. And the perturbed point is also inside the circle. So any score that the perturbed point has is higher than the lower bound for the clean point. Yes?
Okay.
So if the clean point is covered, any score inside this region is also covered, including the perturbed input.
Okay, yeah, got you. Thank you.
Right. Anytime. So is there any other question, or should I?
Sorry. So you mentioned that the calibration lower bounds are exchangeable.
With the test lower bound, with the clean test lower bound.
But will they be exchangeable if the noise is itself not exchangeable?
Yes, because so first of all, now the setup that I mentioned in the conformal layer. So there is this conformal layer that I say there is a 1 minus alpha probability, and then I try to remedy the noise for that. Even in the previous case, if you remember, I said that there is this I don't know, conformal thing. The test point is after this with one minus alpha probability, and by upper bound I'm remedying this perturbation somehow. And now again the same thing happens. So the clean test point in the lower bound score is exchangeable with the clean calibration points in the lower bound. So on the clean point I have the 1 minus alpha guarantee. But now I know that any point inside this region is above that number. So basically also any perturbed input, regardless of whether the noise is exchangeable with anything or not, as long as the noise is inside this circle around the input, it's still covered.
Okay.
All right. So this is for the evasion setup, where I assume that my calibration points are clean, and now I want to be robust to any noisy test input. Also, let's consider the poisoning setup. So recalling the procedure in conformal prediction, I have some scores, I take the alpha quantile. So assume that now I'm an adversary and I want to decrease your coverage probability. I want to increase miscoverages. What can I do at the end? Whatever I do, I should move this quantile as right as possible. Because if I move this quantile to the right, the probability of something being rejected is also increasing. So the probability of true labels also increases, to be rejected also increases, and I decrease the coverage guarantee. This is basically what I do as an adversary. And now as a defender, what do I do is the exact opposite problem. So I try to minimize this quantile by solving this problem. So I try to minimize this quantile in such way that, again, if an adversary tries to perturb anything, whatever they do, I still remain before this quantile. So I still remain before the vanilla quantile. So here I assume that the adversary can change at most k calibration points. So I try to perturb points in such way that I move the quantile to the right. But again, I say that as a defender, I try to find any k possible perturbations that moves my quantile to the right side now, because I want to be more conservative. And by solving this problem, basically I'm finding any possible perturbation, any possible set of k perturbations. And therefore, if my calibration points were perturbed at the first place, I somehow remedy that. And again, with the setup that I mentioned, that I assume that my scores are between some upper bound and lower bound, again, we can solve this problem. We can say that instead of trying to perturb X to get lower scores, I know that there is a lower bound and upper bound, and I can say at worst, the score could move to its lower bound. So I can just solve the problem again with a mixed integer linear program. But now, so far, whatever we said about robust conformal prediction was based on this assumption that there is a function or there is a oracle that gives me a lower or upper bound. But now the question is, how can I compute this lower or upper bound? First of all, I want my method to be working with any black box model. So basically, I'm not allowed to look at the mechanics of the model. I cannot look at the parameters of the model. And second, since my machine learning models are often complex, it could be that inside their score function, if you look at the score function around my point, there are too many jumps and changes. So even if I want to find any kind of lower or upper bound, I might end up with really large intervals that could be useless at the end. Because remember, I want to be robust, but at the same time, I want to be efficient, meaning that I want least possible additional labels to have this additional robustness on top. So then I cannot look at the mechanics of the score. One, because I cannot, based on the definition of the problem, it's a black box. And two, even if I can look at it, it could be a complex model that has really large intervals of upper bound and lower bound. But to remedy that, I can look at the smooth score. What do I mean by smooth? So assume that I have a point X. Instead of looking at the model's result at this point, I add a random noise around it. So it could be a Gaussian noise, for example. And I look at the expectation of a score on this Gaussian mass around the point. So for example, assume that I have an image. I try to perturb this image with Gaussian noises, IID. And then I look at the average score of the model on all these points. All right. So one, it allows me to, later I will tell you how, but it allows me to define model agnostic bounds. And two, if I do this smoothing, I'm basically making these jumps and everything a smooth function. So in many cases, I can also shrink this upper bound and lower bound, and I can get useful bounds here. Is there any question on this part? And I can then proceed. I think not.
Yeah, we are good.
Okay, so then I want to find these bounds through a smoothing. So first of all, I said I cannot look at the function. I cannot look at the function's mechanics. So I don't have the score function and its parameters. I can use it as a black box. So instead of saying that how much this smooth score would move or change if I go to any other point in this perturbation ball around my point, I want to say that what any score function, how any score function would change. So again, let's assume that I want to find an upper bound. So my question is that for this given x, in this ball around it, in this L2 perturbation around it, I do this smoothing and I compute the score and I start to move anywhere in this space. And what is the maximum score that I can get? But I know that this number is lower than if I ask that within this smooth point, how any function would change and what is the maximum for any score function with the same upper and lower bound, with the same endpoints of the range. So assume that I have a softmax. I can say that instead of softmax, I look at any function that returns something between 0 and 1. And I ask that how this function would behave in this region around me. So I know that the maximum of this function is higher than the maximum of my own classifier. Why? Because my own classifier is a valid solution in this space. So my own softmax is also a function between 0 and 1. So I can say that it's also a feasible solution in the second problem. So whatever I get here, it's an upper bound for whatever I get for the first problem at the first place. But now you might say that now that you allowed to move to any confidence function, you might make the problem really trivial and it would just return its maximum possible value, which is right. So we need to add more constraint to this problem in such way that the answer would still contain my own classifier. So the solution would be a valid upper bound to my own classifier's upper bound. But still, with the propagated information, with the leveraged information that I have from my own classifier, I can limit the space of functions to those functions that are close to my own classifier, and then I can have a tighter bounds. So one possible constraint that we can add is that we can say, instead of looking at all space of functions or all classifiers or all models, just try to find this maximum within all functions that have the same mean around my own class, around the point that I have received, with the mean that I can compute from my own classifier. I might say it in a more complex way, but assume that I have my classifier in a black box way, so I can compute the mean score with this smoothing scheme that I defined. And now I say that when are you looking at all possible hypothesis functions or all possible score functions, you should remain in this zone that have the same mean result as my classifier in the point that I have received and seen. Okay, so basically it means that if this is my classifier that you can see, among all possible functions, I just look at those that have the same mean around the given input. And then for those functions, I look at the worst point, like the least possible score that they produce, or the maximum possible score that they produce for the minimum and maximum, for the upper bound and lower bound. So this is a method in one of the robust conformal prediction approaches. But the issue with that is that the mean on its own is not a really limiting criteria. So there could be a lot of functions that have the same mean as my classifier, but they can result in different values. So basically my search space is really a lot, and my upper bound and lower bound are not that tight enough. What we say is that instead of looking at the functions that have the same mean, look at the functions that have the same CDF. So instead of computing this mean and trying to search for all functions with the same mean, compute the CDF, or in a discretized way, compute the discrete CDF, saying that I want this function that you're trying to maximize upon to have the same mass between, I don't know, 0.2 and 0.4. So the algorithm is easy. I have my point, I have my received point, I compute the smooth distribution of my classifier for some bins, I look at the mass of each bin, and I add this constraint on the classifier that is in the second problem to have the same mass inside this bin for the point X. And as you can see, I'm basically limiting the search space to a really smaller space. And therefore, I might have tighter bounds. So let's just recap that what this method has to compare to the other bound. So if I have a smaller search space, I have a tighter bound. And therefore, if I have tighter bounds, I have scores that are less unnecessarily conservative. So I know that the upper bound in the case that I was talking about, the test time robustness, I was looking at the upper bound, but this upper bound is always higher than any score in here. But I could be conservatively high for too much, that I include labels that I don't need to. But if I use the CDF bound, I can limit this just to the points that I need for this robustness. And therefore, my set sizes would be again smaller. And now, again, with the same discussion that we have for the calibration time robustness, as in the evasion time, I have tighter upper bounds. In the calibration time, I have tighter lower bounds, which means that they're higher. So the conservative quanta that I was computing is higher. Therefore, I have smaller set sizes. I'm less unnecessarily conservative. And also, what is the difference between the calibration time robustness and the test time robustness? So as I mentioned before, computing, I don't know, for example, for ImageNet, computing 1,000 upper bounds is like too much. So maybe instead of computing this 1,000 upper bounds, I can compute, I don't know, 100 calibration points lower bounds. So I'm really quicker in the speed of computation in the test time. And as you can see, so for example, for 100 test points, we already gained a lot of computational efficiency. But also the test time robustness hurts the prediction set size as well. Why? Because as I mentioned before, you need to compute a mean or you need to compute a CDF. But the way you compute the CDF is through Monte Carlo samples. While for the bound, you need the true mean or the true CDF with infinite samples. So basically, when you have Monte Carlo samples, you need to also account for finite sample correction. And when you have a limited number of samples from your data, let's say you have 1,000 samples or 10,000 samples, if you want to compute this, these upper bounds for all test labels, so for example, in case of ImageNet, again, for 1,000 different samples, for 1,000 different classes, with the same set of samples, you need to account for Bonferroni correction because you're using the same sample for 1,000 different statistics. So basically, the bounds that you get at the end for this finite sample correction is less tight, and therefore you have higher upper bounds again. So the calibration time is better in these two divisions. One is the computational time because you need to compute less bounds, so less computational overhead. And at the same time, because you have a limited number of Monte Carlo samples, if you compute just on the true labels in the calibration time, you can have a higher efficiency because you can have tighter concentration bounds. So to just summarize our results, basically we compared our approach with the state-of-the-art RSCP, which was working with a mean bound. So our approach is maintaining the same guarantee with very smaller set sizes. We tested on CIFAR10, ImageNet, and Cora ML, which is a graph. And for the graph, we use the sparse smoothing approach, which just accounts for different smoothing probabilities, different sampling probabilities for edge addition or edge deletion or attribute addition or attribute deletion. And we beat the other approach in all these three data sets and all score functions. And we maintain the same valid guarantee. And at the same time, we also work better for all different levels of smoothing. So about this level of smoothing, it's like the sigma in the Gaussian distribution. So if you increase the sigma in Gaussian distribution, you have a larger average around the point. So you might maintain more robust, but at the same time, you're losing some efficiency because you're looking at a larger radius around the point with this higher sigma, so you might lose some sort of efficiency at the end. And this was a discussion on our work. So I'm now looking at the questions.
Thank you very much, Soroush, for the presentation. The audience, does anybody have any questions here from the audience? Okay, maybe I can ask one question. So I didn't quite understand how you calculate the lower bounds. So
okay.
Upper bound was clear. You assume some circle around the true label. You can use the radius of that circle to to calculate an upper bound on conformal scores in the presence of noise. But then low bound, it was not clear. I couldn't understand that.
So the point is that how we compute the upper bound is that we first try to solve this maximization problem. We cannot solve it because it looks at the model's mechanics. So we solve this problem, which is allowing this additional degree of freedom over the hypothesis functions, that the classifier on its own is also one subset of this, one element in this space. And then we say that whatever we get here is higher than whatever we get here, and then we try to solve it with adding constraints here. The same thing happens for the lower bound as well. So we want to search for minimum again here. So we want to search for the minimum inside this perturbation radius. And this minimum is less than the minimum if you assume that your function could be any function. So the same minimization problem now with a different order. So the minimum with any hypothesis function is less than the minimum with this particular classifier. And again, I solve the same problem.
This circle that you assume, the center of that circle is the clear label, right?
The center, so it could be either the perturbed point or the clean point. For easier notation, we can now assume that it's the clean point.
Okay.
Or let's say any point even. It's better to say any point. So for this point I received, I can compute this. I try to compute this maximum around it. All right, and this maximum is less than the maximum if I say that instead of my own confidence function, I have any other function, any other possible function. So the same thing happens also for the minimum, because my classifier is a valid element inside this space. So again, the minimum of allowing any point in the perturbation space for any classifier, again, is less than just saying that the minimum around this point for my own classifier. And sorry, I forgot that. So because I wanted to not to extend it too much to technicalities, so for the Gaussian perturbation, we have a closed form solution for this problem. So and it's in a paper called Certifying Confidence via Randomized Smoothing, I think. And also for the for the graphs and sparse smoothing, we also extend another work that concerns with the mean bound and the binary certificate. We extend their work to the confidence certificate through solving a linear programming that could be solved greedily. So that's the point. So these problems have some kind of closed form solution. I forgot to say that. Yes.
All right. Well, thanks for the answer, Soroush. Faisal, you asked for resources on the conformal prediction. I will put this playlist. You can feel free to check that out. So he asked about resources on conformal prediction. Yeah. All right. If there are no other questions, I think we can thank our speaker again. Go ahead, Christine.
Yeah, sorry, Mari. It's not really a question, but I'm trying to think, because a very, very wonderful work and talk. I really appreciate.
Thanks.
The first thing is about, I see it's really related to inductive conformal prediction. So I'm trying to think, is it the same? I mean, the methodology is still valid for other kind of conformal inference. For example, if you try, so you get the same efficiency. That is my
So I see. So the point is that the framework on its own is basically, I'm not. I think I'm sure to say that the method works regardless of whether you use the split conformal prediction or full conformal prediction. But the whole idea is that if you have this guarantee at the end based on comparison of some score and some quantile, then the whole argument follows regardless of how do you compute these two things. So at the end, it works, I think, regardless of that. So there are a couple of different methods that you can apply conformal prediction. The mostly used one is a split conformal prediction, which we use also in this work. I'm quite sure that we can compute.
I mean, my question is mostly about for example, if you test for using other kind of conformal prediction method, my question is mostly about the efficiencies of the method. So in terms of interval, are you sure that you are getting the same length?
Oh, the same size interval, you mean?
Yeah, that is mostly my question.
So the prediction, so basically your question is that does the prediction set size increase or not?
Yes, exactly.
So it would increase. For sure, it would increase because so at the end of the day, you're more conservative. So if I take this slide, so here, assume that this is the true test point that you have here. I don't know if the selection can be seen or not, but the true test point is somewhere and you are looking at a higher score. So basically the probability of adding more labels, for each label, the probability of it being inside the set is higher. Therefore, the prediction set size would always be higher. This is for sure. But because you're being conservative in this case, you're trying to account also for the worst case noise. But the question is that how conservative do you need to be? So it might be that for this level of noise, I need to be, I don't know, this much conservative, but the other methods are higher in the conservativeness. So we try to be as least unnecessarily conservative as possible, because this conservativeness on its own is adding more labels to the set, and therefore the efficiency is decreasing at the end, or the set size basically increases.
Yeah. Okay. Great. Thanks. And also, sorry, I'm really excited by this. So I don't know. Did you also test for the case where, for example, the perturbation is only coming from the label? So, for example, only the label are affected by the perturbation.
Can you elaborate more? So I don't know what is the label.
Sorry, label.
Yes. So actually, I didn't want to mention it just not to extend the talk too much. But yes. So here we address the feature poisoning in this slide, but the same result we also have for the label poisoning.
Okay. Is it possible to get the paper?
So the paper is titled as Robust Yet Efficient Conformal Prediction Sets, if you ask the name of it, and it was in the ICML 2024. But so we actually also address the label poisoning here, but the difference between the feature poisoning and the label poisoning is that this upper bound, lower bound discussion that I make is for the feature poisoning, not for the label poisoning, because there you are just switching from one label to another label. You're not changing anything in the feature space to capture how much the score would shift. So basically, there also you should solve a mixed integer linear program to get the certified 1 - alpha coverage.
Interesting. Thank you very much.
Thanks a lot.
All right. Well, thank you, Soroush, again for the talk. I think there are no further questions. So with that, we can end this talk.
Great. Thanks.
Thank you.
Thanks. Bye.